Trying to figure out where fire energy came from and magnetic field. Try to catch flare and remap it to some different. It's got a float in the top filter. Performance with this whole tube floats. It's still
Okay, shall we start? Okay, hello everybody. It is 7 o'clock. We're going to start right on time. So I'm Dave. I'm your host here. Before introducing the first speaker, I want to just make a few announcements. Number one, apparently this establishment has been sold, and we haven't talked to the new owners, so if you plan to come to Astronomy on Tap next time, make sure you check the social media or the home page as to whether we actually have it here or we're going to set it up somewhere else. Number two, I wanted to mention that we're always looking for speakers. And speakers don't have to be astronomers. They don't have to be Lowell employees. And we would love to have anybody speak on topics related to astronomy that are just interesting and fun. And soon we'll try to set up something so it's easy to push a button, sign me up. But in the meantime, I guess either contact me directly or send an email to my account at Lowell. I'm Dave Sawyer, so my email is bsawyer@lowell.edu. Feel free to send me an email if you have an idea or are interested in talking. Okay, now number three. This is our anniversary. It was a year ago. A year ago, we started Astronomy on Tap here in Flagstaff, and it's been a fun year, and I hope to keep this going and have a lot of fun. And in celebration of the fact that it's our anniversary, we have two great talks, kind of related to celebration. The first talk is Alcohol in Space, and the second talk is called A Pint of Neutrinos. The way this works, we have two talks. The first one starts at 7 or 7:05, and the second one starts at 8, and in between we have a trivia session. So get ready for that. I'll give you instructions after the first talk on the trivia. So with that, I would like to introduce our first speaker, Dr. Michael West, who is a staff astronomer at Lowell and is also the Deputy Director of Science. And he's going to tell us about alcohol in space. Let's give him a hand.
Thanks very much for coming, everybody. Can you hear me if I don't use the speaker? Or would you like me to use the speaker? Okay. All right, if you can't hear, let me know. When Dave was asking for speakers, especially for the anniversary of Astronomy on Tap, I thought, well, what better topic than alcohol in space? And you might be asking yourself, well, what do astronomers know about alcohol? It turns out quite a bit. There's always been a connection between astronomy and alcohol. Dom Perignon, who is credited with having invented or discovered champagne, is reported to have said when he had his first sip, "Come quickly, I'm tasting the stars," right? In fact, that's a bit of a story, of course, but he was trying to get the bubbles out of wine, essentially. Back in those days, the pressure from the bubbles would increase until the bottles actually blew up, so they were trying desperately to remove the bubbles. And so he realized, it's actually pretty nice with the bubbles, and so he's credited with that. Oh, sorry.
Oh, mine.
Almost 4,000 years ago, there were two Chinese astronomers who failed to predict an eclipse of the sun. And back in those days, people were very fearful. They didn't understand what an eclipse was. So when it looked like the moon was swallowing the sun, they would get out and they would bang pots and they would make noise to scare it away. Well, these two astronomers apparently were too drunk, so the legend goes, to let the king know about this, or let the emperor know about this, sorry. And so they were executed as a result because of their drunkenness. If you've ever seen a Nicolas Cage movie, you know that one word that's never used to describe Nicolas Cage's acting is nuanced, right? So here's a movie, I don't know if you saw it, a lot of people didn't apparently. It's called Knowing, it's from 2009, and it's about the end of the world. And so in this movie, Nicolas Cage plays a professor of astrophysics at MIT. And so what he spends most of his time doing is this. He spends the whole movie drinking in one form or another. So he was a drunk astronomer for most of this movie. There's a very well-known astronomer named Brian Schmidt who won the Nobel Prize in 2011. He was one of the people whose research showed that the universe is not only expanding, but it's accelerating, it's speeding up as it expands. But he's also a very dedicated wine grower. He's been producing wine in Australia, where he lives, for many, many years, and he's a very exclusive brand of wine. He sells only 3,000 bottles a year. Right, so very exclusive. But he said, after winning the Nobel Prize, that was pretty good for business. Everybody wants to have a bottle of wine from the Nobel Prize winner, right? Oh, yeah. Anyway, so he's a music. But the ultimate party boy was an astronomer named Tycho Brahe. If you Google drunk astronomer, this is the guy that comes up. I'm not joking. Try yourself. So Tycho Brahe was an amazing astronomer and an even more amazing drinker in many ways. He's best known for his observations of the motions of the planets. This is before telescopes existed. This is in the 16th century. And he made meticulous observations of where the planets were in the sky. Ultimately, these observations were used to show that, for example, the planets don't go around the Earth and the sun doesn't go around the Earth. Instead, everything goes around the sun. So he was a really pioneering astronomer in many ways. But he was also definitely a character. He was one of the wealthiest men in Denmark, and he got into a lot of escapades. To start with, he got into a duel once, and this is what happened. He got his nose cut off. And when you look at pictures of Tycho, he had a fake nose. He had a prosthetic nose made out of metal. And you would carry a box of adhesive or glue with him everywhere he went, so in case his nose fell off, he could glue it back on, essentially. So when it looked like he was about to sneeze, people ran for cover. But he was, that was one of the consequences of this kind of crazy days. But there's more. He also had a dwarf, a little person named Yep, who lived in his castle. Like we said, Tycho was one of the most wealthy people in 16th century Denmark. He had a castle, and he had a court jester named Yep, who he believed was clairvoyant. And whenever he had dinner, he would make Yep sit under the table for the whole dinner. Believe it or not, he also had a pet elk. I'm not making this up. He had a pet elk, and the elk was fond of beer. And unfortunately, it was too fond of the beer. One night, it drank so much beer that it fell down a flight of stairs and it died. Alcohol probably killed Tycho too. The story goes that Tycho was at a fancy dinner with noble people, and there was a lot of wine, a lot of food, and he really had to go to the bathroom. but he was too embarrassed, he thought it was a social faux pas, to excuse himself to go to the loo, so he held it. And eventually, so the story goes, his bladder burst and he died a few days later.
Oh my goodness.
Alcohol was the demise of Tycho, probably, in the end. So the whole point is just to show you, astronomers know a thing or two about alcohol. I'm going to show you a little bit more about that tonight. What is alcohol? So there's different kinds of alcohol, right? You know, there's methanol, there's ethanol, there's vinyl alcohol. But the alcohol that you are drinking now, for example, is what we call ethyl alcohol or ethanol. It's super simple. It's an organic molecule, and it's made from 6 hydrogen atoms, some gray ones, 2 carbon atoms, that's some blue ones, and 1 oxygen atom. So it's very simple. And it turns out those are some of the most common types of atoms in the universe. They're everywhere. They're in you and me, right? And they're all throughout space. Where did those atoms come from? They came from stars. Astronomers know that stars are they're atom factories in a sense. They take simple atoms like hydrogen, that's the simplest atom, and they transform them into more complex atoms like carbon and oxygen and nitrogen and iron and everything else. And some of those stars, after they finish doing that, they explode. This is what we call a supernova. And they scatter their atoms throughout space. So now you've got space being enriched over time with more carbon atoms, more oxygen atoms, etc. Some of that stuff becomes new stars, new planets, maybe new people as well. That's where we came from. So you carry within you the ashes of dead stars. You carry within you atoms that other stars produced billions of years ago, and they're now part of you. It's a little saying by Carl Sagan, and it sounds kind of cliche, but it's really true. We really are made of stardust. So that's in you, and it's also in what you're drinking right now. Whatever you're drinking right now that is alcohol, it has carbon, oxygen, hydrogen, nitrogen, etc. in it. So you're drinking a glass of the universe in a sense. And as those stars explode, that stuff gets distributed all throughout space, and it collects over time into what we call clouds of gas and dust. This is a photo of one. And from those, new stars eventually form, like this. This is a group of stars. And then planets around them, and living creatures perhaps, comets, asteroids, the whole thing, moons. It's very, very common. A few years ago, astronomers actually measured the composition of one of these giant gas clouds called Sagittarius B. And we can do this by looking at the light that we receive from the cloud. It actually carries information about what the cloud is made from. I can tell you more details about that if you want to know later. But astronomers discovered that in this giant cloud of gas, there's not only alcohol, the kind that we drink, ethyl alcohol, there's enough to make 400 trillion pints of beer. So to put that in perspective, if every person on Earth drank beer every day, it would take you 1 billion years to drink that much beer. And it's actually if every person drank 300,000 pints a day. It started.
Wow.
So there's a lot of beer. There's a lot of alcohol out there in space. And again, like I said, there's lots and lots of these clouds of gas and dust everywhere. These are made of the ashes of dead stars. But over time, complex molecules start to grow, maybe even the stuff of life, right? One thing the universe has is plenty of time. And over time, atoms drift together. Sometimes they stick. They form ever larger molecules, ever more complex molecules, including ethyl alcohol, if given enough time. This is a nice illustration, animation from NASA, what it might be like to fly into one of these clouds. Let's try it again, sorry. There we go. So we're just going to zoom in for a second and see what it's like. It's like, imagine you're on an airplane, right? Flying over through a cloud, but now this is a cloud with lots and lots of stars embedded within it. And our sun probably formed in a cloud of gas like this as well. The sun has been enriched by previous generations of stars that came before it, producing those types of more complex atoms. Anyway, this is sort of a mass illustration of what it might be like to fly into one of these clouds. There was a comet that passed near the sun back in 2015. And as it got closer, of course, it got warmer. As it got warmer, the ice that makes up the comet started to melt. And the molecules in that ice start to glow. And by measuring the light that they emit, we can figure out what that comet is made from. And what we found, astronomers found, is that comets also have alcohol in them. And this comet in particular was releasing into space the equivalent of 500 bottles of wine every single second. Right? So the point is there's lots and lots and lots of alcohol out there in the universe. It's a naturally occurring organic molecule, just as there's organic molecules that make up human beings. So let me talk about not only alcohol that occurs naturally in space, but the alcohol that we humans have brought into space, or tried to bring into space, as the case may be. You know, humans have always had a fascination with alcohol, right? Undoubtedly some of our ape-like ancestors, some of the very earliest humans, discovered fruit rotting on the ground. And to make alcohol, you need sugar and you need yeast usually. Well, those occur naturally, so you can imagine a piece of fruit that rots on the ground eventually begins to ferment and you get alcohol, right? Now it's really good. There's archaeological evidence for going back 10,000 years in China for a site where people seem to have been fermenting a rice drink with fruit and other kinds of ingredients. So people love alcohol now for a long time. So if we're going to explore other planets, other worlds, travel to the stars some days, odds are we're going to want to bring alcohol with us, right? It's just part of our DNA. How much do we drink? Well, there was a famous Russian astrophysicist who years ago calculated that in his home country of Russia, Soviet Union back then, the people drank so much vodka every year, if you stack the bottle, it would reach the moon. That many bottles of vodka. So yeah, humans like to drink. I don't know if humans everybody that. But again, like I said, imagine someday as space tourism grows, and people start to travel into these orbiting hotels around the Earth, travel to Mars someday, travel beyond. They're going to want entertainment. They're going to want to enjoy themselves, right? Or go to a resort or something. And so they're going to expect to be able to drink. So how are we going to handle that? So you can imagine someday, tourists on the moon just kicking back, and I think in this case it's a Carlsberg beer. But again, imagine even longer voyages, right? Right now, if we travel to the distant stars, it's going to take not a few years, but it's going to take generations to reach the stars out there. And so, again, given our human nature, given how we've evolved, people are going to want to have some kind of drink or some kind of stimulant, shall we say. And so how are we going to do that? If you've seen the movie Star Wars, which most of you have, you know that the assumption is that bars are plentiful throughout the universe. And all you have to do is find one on the planet of your choice, and you can enjoy whatever you're drinking on there, so living on that planet too. But anyway, it's the famous cantina scene from Star Wars, right? The problem with drinking in space, there's several. One is when astronauts go on the space station, for example, they often report that things don't taste good. That your taste buds change, in fact, your tongue swells. And so things just don't taste the same as they taste on Earth. And so that's a problem if you're trying to brew a beer, for example, what's going to work on the space station. The other thing, well, there's a couple other things. One is, it's not clear how alcohol affects people in low gravity or zero gravity. But the biggest thing, the biggest impediment to drinking in space is astronauts get something called wet burps. And what happens, on Earth, right? So you're drinking your beer now or whatever, and in your stomach, the liquid in the food settles. I won't be too graphic. The liquid in the food settles, and the gases rise because they're lighter, and gravity's pulling the denser, heavier stuff down. In space, if you don't have gravity, or you have very low gravity, all that stuff stays mixed together. And so when you try to burp, it all comes out, and it's really nasty, apparently. People said it, yeah, that's how you but it's a problem, right? And so, for example, years ago, Coca-Cola tried to get the astronauts to drink Coke on the space station or on the space shuttle, and they even provided Coke for them. But the problem was, any carbonated beverage is going to cause problems, right? And so it didn't turn out really well, so there's never been Coke in space since for that same reason. The other reason, of course, is that astronauts don't drink in space is it's strictly forbidden. Just as you can't get your pilot can't get on an airplane, hopefully, if they've drunk anything within like the last 24 hours or so. NASA and the European Space Agency and almost all the space agencies do not want their astronauts drinking because you don't want to have your mental faculties compromised while you're curling around the Earth at 17,000 miles an hour, for example. So it's strictly forbidden according to NASA policy, according to the European Space Agency policy, etc. The only people that don't forbid alcohol in space. Oh, sorry. I was going to show you this first. That doesn't mean there hasn't been alcohol in space. This is Apollo 8. This is the Apollo 8 astronauts. And they took this very famous picture of the Earth as it came around the moon. It's the first time, really, that human beings have seen our planet from far off in space. It's a really iconic image. And so these are the Apollo 8 astronauts. When they were coming back from the moon, they didn't land on it. They went around it. As they were coming back, it was actually Christmas Day, and they had a special meal prepared in their little kits. And one of the astronauts on Earth had snuck this in. Little airplane sized bottles of cognac, brandy. And they were all excited, except the commander, Fred Gorman, the astronaut, told them they could not drink it. And so they had to bring it home. But one of the astronauts, James Lowell, 40 years later, sold this little bottle of airplane-sized liquor for $17,000. Probably paid on the flight. So there is one group that's able to drink in space, and that's the Russians. And if you ever see a photograph or a picture of Russian astronauts or cosmonauts, they're always smiling. There's probably good reason for that. Here's an image from the Mir space station in the 1990s, and they're clearly having a good time. They're 200 miles above the Earth, they're traveling at 17,000 miles an hour, they don't have a care in the world. And it turns out that, according to the Russian cosmonauts, their doctors allowed them to drink cognac on their flights for medicinal purposes, right? And as you know, it doesn't take convincing, alcohol does have health benefits for people, right? It relaxes you, and etc. And so the Russian doctor said it's okay, just don't go crazy. And so they did. And so there were plenty of examples of, even at the International Space Station, it's actually a problem because the Russians want to drink and the Americans say you can't. But there's even some reported stories of the Russians speaking a little bit to the Americans, essentially. However, there's actually been alcohol drunk on the moon. And that was by this guy, Buzz Aldrin, who, when Apollo 11 landed on the moon in 1969, the lunar module descended and landed, he took communion. He'd actually brought with him from Earth, from his church, a communion wafer and a little container of wine. So NASA never announced this because they were worried that people would be offended that there's any sort of religious connection to NASA's scientific activities. So they never said anything about it, but it's become sort of common knowledge now. But he did bring that on the moon surface. So lots of people have tried to capitalize on alcohol and alcohol in space. It's a certain cachet, right? If I told you we've got beer brewed on the moon up here, well, sure, I'll try it. Everybody'd be pretty excited. And so people have tried to capitalize on this. This is a brand of wine that was marketed in 2015 called, appropriately enough, Moonwalker, because they got 3 of the 5 astronauts who walked on the moon, and they're still alive, to sign the bottles. So it was quite expensive, actually. But this wine's never been in space, never been to the moon, but the astronauts who walked up the moon's surface and all signed it. Here's another example of alcohol that's never been to space, but it's all about marketing. So this is a brand of vodka, cleverly called Outer Space Vodka, and it's got a great alien bottle. It's never been to space, but you know when you make vodka, after it's distilled, you filter it through charcoal, and so they added some crushed meteorite to it. So that's a really good selling point. If anybody's a businessman, you can take all this stuff into account. In Chile, there's a wine called Neutrinos, and it's actually made with a piece of space rock. This is a chunk of rock that is believed to have landed in the north of Chile in the Atacama Desert about 6,000 years ago. And so the guy who owns this company is a keen amateur astronomer. In fact, he actually runs an astrotourism observatory in the north of Chile. And then he also makes wine. Chile's got great wines. And so we combine the two. And so what they do is, when they're aging the wine, they drop this moon rock in the barrels for a year, essentially. And I guess it seeps some of the molecules off, or who knows. But it's a great advertising plan. But again, this wine's never been to space or anything like the rock has, obviously. But there is some wine that's actually traveled to space before. Back in November of last year, just a few months ago, a French company, a startup actually, sent up 12 bottles of Bordeaux. And it's going to spend 1 year on the International Space Station aging. And the idea is to see, well, what's the effects of being in space? And you might think, that's stupid. Why would you do that, right? It costs an arm and a leg. What do you learn from that? But the idea is that in zero gravity, or microgravity, very low gravity, things do behave differently. And also exposed to what's called space radiation or cosmic rays. These are high energy particles that are zipping through everything. They'd be hitting you, well, some of them are hitting you and me now, but mostly we're protected by Earth's atmosphere. But in space, these things blast through everything. And so what's the effects of these high energy cosmic rays and other particles passing through the wine over the course of a year or so? They want to find out what the effect is. So like I said, they've launched 12 bottles into space aboard the International Space Station. They need sort of very attractive containers. And they'll spend a year up there seeing what the effects are of zero gravity and cosmic radiation. So that should be interesting. A number of breweries have gotten into the idea of beer from space. This is a company called Dogfish Head, you might have heard of them. And they brewed a beer that actually has crushed moon dust in it. They actually got a rock from the moon, pulverized it, and sprinkled it into the beer, right? Again, clever marketing. It's never been space, but clever marketing. So the best marketers are these guys. It's an Australian company called Pint. And so their beer's never been to space. But they said, look, astronauts, they said things don't taste really good in space. We better make an extra flavorful beer, right? So that's what they try to do. It's actually been a prize-winning beer for them. And mostly they're about the really clever advertising. So there's another one of their ad images, and that's trying to catch one of the bottles of beer. Another one. Here's one of their commercials. I don't think my sound is working. Let's see. Yeah, sorry, it's not working. Well, I'll just show a second of it. Anyway, pretty clever. If only you could hear the sound. Anyways, they're really good at the marketing aspect of it. But they also realized something. If you're good at drinking space, it's hard. Because if there's no gravity, or very low gravity, stuff doesn't pour. So how do you get the beer out of your bottle? And nobody wants to drink beer out of a pouch with a straw, unless you Yes, right. So what they did was they spent a lot of time working with engineers, and they developed a bottle that they claim will actually allow you to drink beer in zero gravity. It has a design that kind of wicks the beer up through the opening. And to prove their point, they actually tested it on one of those microgravity plane flights. You know about these, it's called a vomit comet, these planes that go up and there's these parabolic arc. It's like you're free falling, so it's like you're weightless. They brought these bottles of beer up in this plane and they tested it. And the conclusion was, it works. So it's not gravity fun. So they claim they tested their beer in essentially zero gravity conditions. That's what these are argue their point. There's another beer in from Oregon, and this one is called Ground Control, cleverly enough. And this one, they sent samples of brewer's yeast, the stuff that you use to make beer, up to the edge of the Earth's atmosphere, up to the border with space. Went up 70 miles or so. And it stayed there for a little while, and it came back down, and they made beer from it. And so again, great marketing idea. Now they can talk about their beer that's been brewed in space. Budweiser, you may or may not have heard, Budweiser is vowed to be the first beer brewed on Mars. And so they have actually put their money where their mouth is. A lot of these other companies I was talking about are just sort of, it's a cool advertising gimmick. They've actually sent now 3 different experiments on the International Space Station to try and develop a process of how you might brew beer on other worlds like Mars. So what they did, for example, their first experiment was they actually sent barley into space to see how it would germinate under conditions of zero gravity. And now what they're doing, the next step, is they're seeing how you can malt, right? So you go through this process from grain to malt to your favorite alcoholic beverage or beer. How you can malt barley in space, kind of the next step in the process. So they're really doing these experiments. Just back in, I think it was December, they actually sent their latest experiment up to the International Space Station. So they promised they'll be the first beer on Mars someday. But speaking of Mars, how many people saw The Martian? Almost everybody. So if you saw The Martian, or Matt Damon, what does he need to eat to survive? Potatoes. So he grew potatoes in the Martian soil, and he was able to survive. So it turns out the author of the book. It turns out that one of the things you can make from potatoes, of course, is french fries, potatoes, which you want. You can also make vodka. Right? And so the author of the book says people often ask him, could Mark Watney, the astronaut stuck on Mars, could he have made vodka from some of those potatoes? Just have a good time once in a while. He says that's one of the most frequent questions he actually gets asked. And the answer, of course, is sure he could if he didn't mind starving to death. Because it takes about 20 pounds of potatoes to make a bottle of vodka. And if you're the only guy living on Mars, it's your only source of food, probably not a good way to spend your potatoes, right? Anyway, so there have been a number of other alcoholic beverages launched into space. One is called Moonshot Gin. It was launched up to the edge of the Earth's atmosphere, right up the boundary for getting out in space. And the other is Ardbeg whiskey. It's a single malt from Scotland. So with the Moonshot Gin, this is on one of those high altitude balloons, goes up 100 miles or whatever. You'll see in a second, they actually sent the ingredients for the gin. They sent the juniper, they sent the coriander, they sent the lemon peel, all into space, and then it looks like it's blowing apart, but it's not really. And it's now plumbing down to Earth eventually. And then they use that stuff that had been in space, those ingredients, the botanicals, to make gin, which they were happy to sell to people. But Ardbeg, this whiskey, Scottish whiskey, actually did an experiment on the International Space Station for 3 years. What they did was they wanted to check what the effects were of aging whiskey in zero gravity. So a great quote from them is one small step for gravity for whiskey. That's true. And again, if you think about it, like I said, so for example, you make a whiskey, right? And the good stuff takes 10 years, great stuff you age for 20 years. Why does it age for so long? It's because these are all chemical processes, reactions that occur that make it more tasty over time. Only you can accelerate that somehow and sell your whiskey after a year. Maybe you can do that in space. Now there's a cost issue, it costs a lot to fly your whiskey up and bring it back down. But Ardbeg wanted to experiment with that. And so they sent their whiskey up for 3 years on board the International Space Station. These are actual samples that they sent back, but it wasn't like in a bottle. And they put in little oak shavings to simulate what it would be like if it was actually a cask for that time. And then when it came back down, after 3 years, they actually tested it. They did really, really detailed chemical analysis. It was actually pretty impressive. So it wasn't just how does it taste or smell. They did a detailed chemical analysis, but they also tasted it. And the conclusion was, they actually published a report, right? So it looks serious. The aftertaste is pungent, intense and long, with hints of wood, antiseptic lozenges, and rubbery smoke. The people that they had tasted, and they kept, I should mention, they kept an identical batch on Earth, so they compared the two. And they said everybody blindfolded could tell the difference. So maybe it's not a good idea to age your whiskey in space then. And I just want to point out, if you want to drink something that tastes like antiseptic lozenges, you don't need to go to space for that. The Finns drink something called fisu. I drank it, so you don't have to. What it is they take vodka and they crush Fisherman's Friend throat lozenges inside the vodka. You wait a day and you drink it, and it tastes as you probably imagine, but it tastes throat lozenges basically. So you can get it on Earth. It's really desperate to try it. There's also a Japanese whiskey that in December of last year sent 6 different kinds of whiskey into space to see how they age over 1 year, because they did with the metal from our thing. So they sent an unaged one, a brand new one, all the way up to a 21-year-old Scotch that basically sitting next to the Fisherman's station. So they're waiting to see. And you won't be able to buy or taste that. It's just for them to figure out if it's worthwhile, essentially. And of course, tequila can't be left out. So a few years ago, Jose Cuervo launched tequila into space. The temperature up there, it's the edge of Earth's atmosphere, on the high altitude balloon, is minus 92 Fahrenheit. So they billed this as the world's first frozen margarita. Back onto Earth. So let me just finish up. The main points I hope you take away from this is you really are drinking stardust tonight. The atoms in your alcohol, the atoms in you, were made inside stars. That's pretty amazing. Also, alcohol forms naturally in space. It's plentiful everywhere out there. It may be hard to collect, but it's everywhere out there. It's just a natural organic molecule. And as I said, as the evidence already shows, humans are going to travel to the stars and they're traveling to space. We're definitely bringing alcohol with us. So I'll take there. I'm happy to take any questions if people have them.
Running a little bit late, so we'll take a couple of questions and then move on. Any questions? Bye.
Do you know if those French guys that put the 12 bottles into space didn't drink up all their comparison by the time they got
Never
back
know,
down?
that's right. You can get any 12 bottles, nobody knows the difference.
Other questions?
Michael, do you have any idea, like, what does it cost to send up these samples?
It's crazy expensive, right? And that's the thing, that's why I think it would never be economically viable. I forget what the cost per pound to launch something in space, but it's astronomical. Yeah, and so it can't be worth it, at least as it's currently.
Thanks.
You'd be drinking $1 million bottles of whiskey or something.
One more.
So are you or the Lowell Observatory involved in any sort of alcohol research?
We should be.
It's just a personal
It's
passion.
confidential.
Okay.
This is how we put our foot in the door.
No, but it would be an idea. It's not a friend that was able to have a big accent. We're both big accent fans. Maybe
Oh,
just
okay.
Cincinnati in space or something.
Ooh. That one's
Some of us tried our hand at brewing a few months ago.
That's true, the Pluto beer. Yeah. That's true, yeah. Which was it Dark Skies or who was it? I can't remember.
Mother Road.
Mother Road, sorry. So yeah, that's right. City's trying to get involved in that.
Okay, let's give Michael another hand. Great talk, thank you. Okay, we're going to queue up All right, let's get started with the second talk. I would like to introduce Dr. Kuehn, who is the Deputy Director for Technology at Lowell Observatory, and he's going to give a talk on a pint of neutrinos. With that, let's give Dr. Kuehn a hand.
Thank you. This is going to be a fun one, I hope, because it's actually about my PhD research. So if I have a PTSD flashback and end up going in a fetal position, I'll recover in a few minutes. My PhD wasn't that bad. But I will be talking about the work I did with the Ice Cube Neutrino Observatory. You saw a few pictures of that during trivia. You might not have known what that was, but I will show you pictures. And this is work I did. I graduated in 2007, so it's been a while, but it's always fun to revisit some of the work I did in the past. So to start off, most of you are familiar with photons. That's all the regular light that we use to observe the universe. We have different energies of light. There's gamma rays, X-rays, ultraviolet, optical light, infrared, radio waves. So there's all these different wavelengths of light give us different insight into different parts of the universe. We can see things in infrared that we can't see in optical, and vice versa. But there's also this whole other group of particles out there, not just photons. There's cosmic rays. So these are some of the regular particles you might know, like protons and neutrons. Those are actually made up of more fundamental particles called quarks. So two ups and a down come together to make a proton. Two downs and an up is a neutron. But then in the standard model of particle physics, there's also these other particles. There are the leptons, are the electron, muon, and tau. Muon and tau are basically just heavier versions of the electron. Then we have the neutrino versions of each of these. And these are extremely small, extremely light particles. There's billions of them flowing through you right now, and not a single one will interact with any atom in your body. So they're very, very small. The technical term for this in particle physics is the cross-section, which is the idea that if you think of billiard balls, their cross-section is, like this. Neutrinos have a cross-section, it depends on the energy actually, but it's something like 10 to the minus 34 centimeters in that neighborhood. So they're very, very tiny. So you need zillions of them. That's another technical term, zillions. And zillions of them to even see one interacting. And I'll get to how we do the detection in a bit. But for comparison with normal matter, you would say a pint of liquid like alcohol is a pound, maybe half a kilogram. Neutrinos, if you stuck the same number of neutrinos in a pint glass, it would weigh less than a nanogram. That's 10 to the minus 9 grams. However, if you sort of pack them all in, don't use the same number of particles that there are in a pint of beer, but if you cram them all in to a certain density, you can get much, much more. It'd be more like sort of like a white dwarf or a dense star. If you pack them in close enough, you can get tens of thousands of tons of neutrinos in the same volume. That doesn't generally happen in anything outside of a physicist's imagination. You will get a lot of neutrinos coming out of certain stellar processes like supernovae or active galactic nuclei, and I'll get into those in a bit too. But that's just to sort of set the stage for you. So here we have sort of a cartoon of Earth here, and then you've got a detector inside the Earth. Actually, the funny thing about these telescopes is some of them will point down through the Earth. Like Ice Cube, for example, is in Antarctica, buried in the ice. And we actually look at neutrinos, as I said, they can go through a lot of matter without interacting at all. They'll actually go all the way through the Earth. So if one happens to interact with ice at the South Pole coming from the northern hemisphere, that's a good way to block out all the other particles, because no other particle can do that. So I don't know who first thought of pointing a telescope down into the Earth, but that's how Ice Cube works. So what the advantage of not interacting much with anything is that it can come from places that are extremely high density that you won't get light or any other cosmic rays from, like the center of an active galactic nucleus or a gamma ray burst inside a cloud of dust. All these things will block photons. Magnetic fields will make charged particles come, twist around and come from a different direction from the original source. But neutrinos will just come straight through the Earth. And that's why we can see them. If we can find their direction, we can point back exactly where they came from on the sky, see what's there, and then we learn about the sources like black holes and things like that that we can't see directly in photons. So some of the sources of neutrinos are theoretically proposed. Some of them have already been observed. The first neutrinos we saw were from the sun. And then what really started neutrino astronomy was supernova 1987A. You might know the story of the astronomer in Chile who was out for a smoke one night, looked up, and he knew the sky well enough to say, "What's that new star?" And it turned out that was supernova 1987A. But at the same time, the neutrino experiments that weren't really intending to do astronomy at all, they were measuring fundamental particle physics, the lifetime of the proton. Specifically, they saw a huge burst of neutrinos. Turns out in this case, huge means 11. But when your background is 0, 11 is significant. And then they heard about the supernova and they said, oh my gosh, we had sort of theoretical predictions of that we won't just get photons in supernova, we'll get neutrinos too, and we actually saw them. Let's have a beer and celebrate. That's what started the field of neutrino astronomy. That's what funded my PhD. So that was fortunate. But there are other things that we've not seen neutrinos from yet. But just like supernovas were predicted to come from there, we have gamma ray bursts. We have active galactic nuclei. And I actually lost a bet with my grad school office mate about where we would first see neutrinos from. I'll get into that in a bit. She was working on active galactic nuclei and I was working on gamma ray bursts, and I thought for sure I would win. I'll show you what my results were in a bit. But I already told you the punchline. I lost that bet. And then there's something interesting called GZK neutrinos. That stands for Grayson, Zatsepin, and Kuzmin, 3 Russian physicists who proposed that there would be photons and protons interacting, the photons from the Big Bang interacting with high energy protons accelerated by these huge cosmic explosions. But if they're high enough energy, they'll interact with the photons and create these cascade of particles. You won't get protons above this certain energy. It turns out to be 10 to the 21 electron volts. But you will get neutrinos that will come from sort of everywhere because they're due to interactions with the cosmic ray background. So that is what we built IceCube to detect. This is not actually the IceCube detector. This is what we call a counting house. This is on the surface of the ice at the South Pole. But we take a hot water pressurized drill down about 2 kilometers, and then drop a string of photomultiplier tubes down into the ice, hopefully quickly enough before it freezes back up. That worked for most of the strings of detectors. There was one that it didn't. So here you have the Antarctic, you have the South Pole, you have the runway for the planes that land there, and here is the literal South Pole is right there, just inside the building. And then IceCube is over here. There was a precursor detector called Amanda, the Antarctic Field and Neutrino Detector Array. That was a bit smaller. That was to test out this technology. And that's just across the ski ray from the South Pole. So I'll first show you a schematic of how IceCube is built. As I said, we take 86 of these holes, drill down 2,800 meters, so almost 3 kilometers, almost to the bedrock under the ice of the South Pole. Then we drop these strings down. Use the Eiffel Tower for reference. This is almost 10 times the size of the Eiffel Tower. And we need thousands of these photomultiplier tubes to detect the neutrinos because they create very, very minute flashes of light. So we're not actually detecting the neutrino directly, we're detecting the light that comes from the neutrino interacting in the ice. And we'll get to that exact process in a minute. But this was sort of underway when I was doing my PhD. I said I graduated in 2007, so we were building it. We had the first couple of strings in when I was finishing up, and then it completed after I was working as a postdoc at the Ohio State University. And then it's really taken off since then. So here is the photomultiplier tube is at the bottom. That, as its name implies, it multiplies photons. You get a small amount of light in, and you get generates a huge electric current, and then you can measure the intensity and the timing and so on in what's called a digital optical module. And these are we have I think 8,640 of these buried in the ice. Here is, for those of you who are computer engineers, this is basically the computer board that goes inside each optical module. The analog digital wavefront, the memory, the power supply. We have a flash here on board this so we can test and we can generate our own light to make sure it's working. So this is all sort of the background and how we do the detection. There's a whole stack of these as they're waiting to get hooked up to the electronic cables and drop down into the ice. Here's a bit of the actual install process. Here's the counting house I mentioned where all the electronics and cables go into there, and that's where we do our measurements. Here's the large hose reel. We need about 3 kilometers of hose that's powered by, the water is heated by jet fuel and then pumped down into the hole. So this looks pretty small on this scale, but here it is. Here's a person per scale, so just a comparison. This is 10 meters long or so, something like that. So we have an enormous amount of hose reel that drops down into the hole and creates the hole for us. And then we drop the optical module down into it, drop it about 10 meters, hook up the next one, drop it about 10 meters, hook up the next one, until we do the whole string. Then we go to the next spot over, drill another hole, and do that 86 times. So, TJ, can you play this video for us? This is a schematic of zooming the one optical module out to the whole detector. So here you can see the 86 strings of the detector. And then you can see how far they're below the surface, where all the drill holes are, and the detector counting house, and some very, very distinguished astronomers should be working on ice cream. So,
how long does it take to drill all the way down and get a string placed?
The whole process, I think, is around 24 hours. The drilling is out like 4 or 6 hours, I believe, and then you have to attach the optical modules one at a time and drop it 10 meters. So it takes around a day, I believe. So, and before the hole freezes up, so you gotta have constant. So I think we had like 3 groups of 8-hour shifts to get it all done. Yeah, it's hard work, especially at minus 80 or whatever the temperature is. So we built a little shed around the hole, like an ice fishing hole. But yeah, it's hard work. So I mentioned detecting the light from the neutrinos, but I haven't gone much into the process of exactly how that works yet. For analogy, here is a picture of a sonic boom, which is when an object moves faster than the speed of sound in the atmosphere. The sound waves basically pile up behind the object, and you get a shock front. And the same sort of thing happens with the neutrino. It will interact with, in this case, a muon, and the muon is traveling faster than light in the ice if it gets enough of a kick from the neutrino. But wait, I hear you saying, I thought things couldn't travel faster than the speed of light. Which is true, but I said the speed of light in ice, which is actually just a little bit slower than the speed of light in vacuum. So you can actually get particles traveling faster than the speed of light in ice. And if, like I said, if the muon gets enough of a kick from the neutrino, it will do that. And that will also produce a shock front. it will be, instead of a sonic boom, it will be a light boom. So what we actually detect is not directly the neutrino, we detect the light that comes from the muon that comes from the neutrino. And as you can see, it's a cone shape. And here's sort of the chemical equation, if you will, of a neutrino interacting with most likely an oxygen molecule in the ice. The oxygen in H2O is much, much bigger than the hydrogen. So interact with oxygen, it will create an electron or a muon or tau, depending on the flavor of the neutrino, and then that will generate photons as it travels. So you can see the interaction here, the particle traveling through the detector and the shock front. So first this detector will get lit up, and then this one, and this one, and then this one. And then we measure the timing of this to reconstruct the track. If you could play this video, it shows you how to do that. So you see the neutrino in red, the muon in yellow, and then proceeding through the detector and the color codings gives us the timing of the event as it goes through the detector. So red is first, all the way to blue at the end. You saw the electronic signals go up to the surface, and then we correlate all the signals in, they're separated by microseconds basically, or milliseconds, and then we have to, as I said, know which one got hit first and which one got hit next. Then we know the track of the muon, which tells us the track of the neutrino, and then we go look up at the sky and say, what's over there? And this is basically exactly what they did with gravitational waves. They could sort of locate it to a big region on the sky, and then we went and looked with satellites and regular telescopes. We look with photons and see what's over there. In the case of gravitational waves, they found a black hole. In the case of neutrinos, we're still working on that, but as I mentioned earlier, I was looking specifically for neutrinos coming from gamma ray bursts. So if you have a gamma ray burst go off, that's a star collapsing down into a black hole and releasing most of its energy in the span of, well, it's the entire rest mass energy of the sun. So the sun will last for about 10 billion years, and there'll still be a bunch of it left over. Think of all the light that the sun puts out in 10 billion years over the duration of about how long you can hold your breath. That's how long gamma ray bursts last, and they put out that much energy. So we expect a lot of photons and a lot of neutrinos. So we can either look for the neutrinos first, and then correlate it with photons, or we can look for the photons first, and then go back and say, now that we know where the gamma ray burst is, do we see neutrinos from there? So we had the Compton Gamma Ray Observatory and the burst and transient source experiment on it, and then we had the Swift satellite, that's still up and running. But we have these. So what I did is I started with the photons. I looked where these gamma ray burst detections came from, and then I said, okay, let's look back at that portion of the sky in this time window when the gamma ray burst was observed, and what do we see? Any guesses what we saw? No? Anyone wants to take a wild guess? So this was the punchline from my PhD thesis.
Absolutely nothing.
So yeah, I literally, out of the hundreds of gamma ray bursts I searched for, I saw 0 neutrinos, which it turns out was an interesting result. It was a little bit disappointing. I wanted to win that bet and be the first one to detect a specific source of neutrinos that we could point the neutrino back to. I mentioned that we had seen neutrinos in supernova 1987A before, but we couldn't actually point out where the neutrinos came from the neutrino tracks. We just knew that there was coincident in time, and that was the only thing going on in the universe we could see. So it's a correlation in time, but not in space. Whereas this is actually detecting sources of neutrinos in space other than the sun. But as I said, unfortunately I saw 0, but that was still interesting because there are a lot of theories out there that were predicting these are huge explosions, more powerful than supernovae. We should be seeing neutrinos. If this is what's going on inside the gamma ray burst, we expect 1 neutrino, 10 neutrinos, 100 neutrinos. There's all sorts of different theories. And I proved several of these theories were not viable. Of course, then the theorists are good at coming up with excuses or reasons for why we didn't see something as well. So then they said, oh no, wait a minute. This theory down here predicts just a little bit less, just a little bit fewer neutrinos. So you could set this limit, if neutrinos were coming from gamma ray bursts, you would see this many. So instead of 1 or 10 or 100, how about 0.2? Yeah, that's a good number. We expect 0.2 neutrinos. And then, so after my PhD thesis, I handed this off to another grad student and another one after that. And eventually we caught up with the theorists. So here is, in some very strange units, the flux basically, this is the number of neutrinos from gamma ray bursts. Here are various theories. And then after IceCube went from the prototype Amanda detector to 40 strings to up to 59, once we combined all that data and still saw no neutrinos, then we could say, well, here's our limit. If gamma ray bursts were producing neutrinos, we would have seen neutrinos up to this number. These predictions are higher. If you consider this, say, 1 neutrino, these were predicting 2 or 3 or 5. And so we could rule out these theoretical models. There's still some that effectively predict 0 neutrinos, so those are safe, pretty much untestable at this point, as far as neutrinos are concerned. But we, with enough data, we ruled out most of the leading theories of where neutrinos are coming from, which becomes, at the very least, we know they're not 100% of the neutrinos that we can see. 100% of the cosmic ray acceleration that might lead to neutrinos is not coming from gamma ray bursts. The other main idea is active galactic nuclei. So that's where people turn to next. We started seeing with IceCube, once we had the bigger detector, we started seeing really, really high energy events. This one wasn't the track going through, it was just sort of an explosion right in the middle of our detector. So the energy is of order 1 peta-electron volt. So a GeV, I'm going to have to remember this. GeV is a billion electron volts. TeV, EeV, PeV, so 9, 12, 15, 10 to the 18 electron volts. So a single particle with that much energy, that's, I think that's about the kinetic energy of a well-hit golf ball. So that, and a single particle. So if that hits you, you might know it. And we've seen even higher energy particles since then. So these were, once IceCube was fully up and running, we saw some of these, but there's no directionality to this. It's just in the middle of the detector. We can't say, oh, the track came in from over here. Let's look over there and see what we can see. But then, more recently in 2017, that's when things started getting really interesting. There was, as I mentioned, the only place we've really detected neutrinos from astrophysically is the sun and supernova 1987A, but again, that was just because they correlated in time. We can't really point a neutrino detector at those things. But there was a neutrino that was detected that corresponded in time and in position with a gamma ray blazar, which is a black hole at the center of a galaxy. So it was only 1 neutrino, so that got a lot of particle astrophysicists excited to get a convincing signal of 3 or 5 or 10 neutrinos. I mentioned 11 was an overwhelming signal. You need to start with 1. So they found 1, and then that caught their attention. They went back and looked at this blazar, and it turned out there was a flare from the blazar several years previously that also corresponded to a group of neutrinos, some people are convinced that this is smoking gun evidence that neutrinos do in fact come from black holes at the center of galaxies. In statistical terms, the result was 3.5 sigma, which for particle physicists, 3 sigma is evidence, 5 sigma is a concrete detection. So it's sort of in the intriguing neighborhood. A lot of 3 sigma detections in particle physics have gone away. In the past, they were just a statistical fluke. It's 1 in, I think, 10,000. So if you do enough experiments, you're going to get it happening randomly. So that's evidence for this, but it's not complete proof yet. I think this might be the solution. I was willing to concede that I lost my bet when I saw that this active galactic nucleus was correlated on multiple different occasions with a neutrino, but stay tuned. the IceCube people will be updating their results in the next couple of years, and it'll either go away or it'll be definitive proof that yes, we've seen neutrinos from these sources. So I could not have done my work without my IceCube collaborators spread all over the world, in Europe, in Japan, in Australia, New Zealand, and as we saw during trivia, there are several other neutrino detectors as well. The Baikal neutrino detector is in Lake Baikal in Russia. The Antares detector is in the Mediterranean off the coast of France. Much more hospitable venue than Antarctica. But you have lots of other problems with that one. If you're looking for minute flashes of light, you might get bioluminescent organisms that can create noise in your detector. So whereas there's none of that in the Antarctic ice, so it's a much purer signal, but it's a lot harder to build. So there are trade-offs for all these different neutrino detectors. The other advantage at the South Pole is if you're looking through the Earth, you're seeing the entire northern hemisphere all the time, whereas these others are sort of spinning with the Earth. So if you're looking through the Earth, you're seeing different things at different times. So they're really complementary techniques. So you might want to go away and Google Antares and Baikal as well as IceCube, and it'll give you a lot more sort of comparison of these different technologies and how what sort of results they're getting, whether anybody else has found neutrinos from sources or not. There's also other neutrino detectors at lower energy. There's the Submarine Neutrino Observatory in Canada. There's a superconductor detector in Japan, which also has a very interesting sort of nuclear non-proliferation and national security aspect, because it's located so close to North Korea, and it looks at lower energy neutrinos, the kind that come from nuclear reactors or nuclear explosions. We can actually take superconductor data and see when the North Koreans are doing nuclear missile tests. So there's a lot of interesting sort of reactor and neutrinos and things like that. That is a whole different talk. I'd be able to come back and talk about those at some point too. But this is where we're at. This is the current state of neutrino astronomy. So thank you very much for your attention. And as I answer questions, here's a couple more pretty pictures from the South Pole.
There's a fighting.
Very cool, pretty pictures.
Questions? Yes.
Tyler, I remember back in the mid to late 60s, that's a long time ago, so my memory's fading. But there was this really big problem with the solar neutrinos.
Yes.
And I forget, it got resolved, but wasn't there more than one type?
Yes, so that's where these different flavors of neutrinos come in. There's a prediction given nuclear fusion inside the sun, we knew how many neutrinos it should be produced and given the number of photons. We were only seeing about half of that. And one of the grandfathers of neutrino astronomy, John McCall, said, hey, wait a minute, what if there's just other kinds of neutrinos we're not seeing? It was a heck of a lot of effort just to see this first kind. We know there are these different flavors. We know there are electrons and muons and tau particles. We know there are these other types of neutrinos as well. What if they can swap flavors? What if our vanilla neutrino can become a chocolate or a strawberry and we can't detect it anymore? Because our neutrino detectors only detect one flavor. And the entire community was like, no, that's garbage. We don't believe that. For probably 20 years. And then, finally, I think it was in like the 80s, when there was first evidence for this actually changing of flavor. It's called neutrino oscillations. So what that means is there's some other sort of fundamental property of neutrinos that you can get one type of neutrino that will switch into this other type. And once that was shown in the 80s, 90s, and 2000s, then everyone was like, oh my gosh, John McCall, you're a genius. I knew it all along.
So it was really the detection. If you could detect them all, there was never been a problem.
Absolutely. Funny story about John McCall. I showed one of my plots, the Waxman and McCall limit. He was one of the ones who predicted a certain number of neutrinos. And I was presenting my work on reaching the Waxman-McCall limit on predicted neutrinos. I was presenting this at a conference, and I started explaining what the Waxman-McCall limit was, and some elderly gentleman in the front of the room spoke up and said, I don't think you have it quite right. I think it's like this. And I said, well, I've been studying this for several years. I've been reading all of Waxman and McCall's papers. And he said, I am John Waxman. So he was very gracious about it, but we had a chat afterwards, and it actually was really helpful for me because it corrected my understanding of the processes he was talking about and why we weren't quite reaching his predictions yet, and it took us a bit longer. It took my predecessor after me to actually rule out his theory, so we still proved him wrong.
Questions?
Tyler, so when you're drilling down into the ice, did you come across anything interesting?
That's a very good question. So when we're drilling in the ice, did we find anything interesting? According to some of the science fiction movies out there, there's an alien spacecraft buried under the ice in Antarctica. We didn't find one of those yet, which is probably fortunate because those were predators. That was a really bad one, Alien versus Predator. It's such a good premise, but the execution is awful. Maybe not quite as bad as, was it The Day After Tomorrow or Armageddon? But in actual answer to your question, yes, so in addition to the particle physicists who are wannabe astronomers, who are studying, not photons, but other cosmic rays and so on, we had a bunch of paleontologists who would work with us too. And the ice, a kilometer down, is incredibly pristine. And it's from millions of years ago. We've just been piling up snow that turns into ice. So yes, there's amazing results came out of the paleoclimatological record. In the first couple hundred years, the reason we went down a kilometer is the top kilometer still has air bubbles in it, which are trapped gases from the atmosphere from 10 billion years ago. We can get pollen grains from the last several million years. So there's botanists, biologists, paleoclimatology, a lot of other science. In fact, we invited some of these people to our conferences when we had our group meetings and showing off our neutrino results. And those were some of the most well-attended presentations. People love the climatology. And like now, we haven't seen any neutrinos yet. I'm not going to go to that talk. Oh, but climatology, yes.
I guess it's obvious, but once you put all your instrumentation down in the ice, it's not true.
Yeah, well, climate change might help with that. But the Antarctic Plateau is shifting by a few meters every year, so I think we're predicted in about 3 million years, the whole ice shelf will be in the Southern Ocean, so we'll be able to retrieve that. Yes, it's basically like operating in space. You can't get it back, you can't maintain it. You can do stuff on the surface, and you can replace it. So some of the, when you're down 2 kilometers down in water that's freezing around you, you might get the ice freezing unevenly, it'll pull out the electronic connections, or the detector might just succumb to pressure and implode if there are flaws in it. So we lost a few of the individual detectors, but whole strings are good, and we can always drill another hole next to it and drop another one. In fact, there are proposals to do just that. The denser packed your detectors are, the lower energy you can detect. So we're detecting sort of billions of electron volts and up. So 10 to the 9 EV, which are the sorts of energies that only come from supernovae and gamma ray bursts and active galactic nuclei. If you want to look at lower energy, actually it's not even supernovae, those are lower energy. So like Super Kamiokande, the light detectors are only a few meters apart. For us, they're 10 meters apart on a string, I think, and about 20 meters from one string to the next, or maybe even a little more than that. So, because you can get a particle going through, and if it's lower energy, it'll only deposit a little bit of light. You might only get one detector going off. You can't really reconstruct a track from one point. So we need higher energy, or we need a denser detector, and so that's the next step.
One last question.
How do you control timing?
How do we control timing? So there is a clock board on each of the optical modules, and we synchronize them. And we know the travel time to the surface, we can measure that. We can send pulses down and back up and measure the round trip travel time and so on. So we know the distance from each detector to the counting house. And then when we get a signal, we know what sort of the time delay was to, again, microseconds, maybe like 50 microseconds is I think our timing accuracy. And that lets us determine the order of the detection of the light through the whole detector. All right, thank you again for your attention.
It's good to have you on here. Thank you again, everybody, for supporting us. And like I said, stay tuned to the social media for the next event. I can't say for sure it's here because of the potential new owners, which are starting in 2 days, and we haven't talked to them, and we don't know. So, so anyway, check the pages to see whether we're meeting in a month.
My neighbor had one question he wanted me to ask here tonight. Who can tell us about Beetlejuice?
Oh boy.
Phil Massey should come next.
I know. Actually, I tried to get a talk on that,
Oh, did you?
but Emily is in Washington, so it's not so easy a distance. But we'll work on
It's
that.
brightening again a little bit. Looks like it's no brighter than relative.
Yeah, it's interesting. So we'll work on that. All right. Well, thank you, everybody. Appreciate it.